All right, well, welcome to another beautiful day of differential equations. So today, we're gonna keep kind of playing around with different forms. We're gonna look at a few more that lead to separable and some tricks that we can play. And then we're gonna look at a completely different classification of first order differential equations that are called exact, and exact have their own method of solving. All right, so that's my plan. Before I do that though, are there any homework questions, anything you want to look at from anything up to this point? All right, Victor, number 12, can you, okay, there you go, thank you. So 2.2, number 12. So number 20, but section 2.2. Okay. Well, let me go and find that and we'll take a look at it. All right, so let me go ahead and share this guy with you. All right, so here's our book. So this is section 2.2, number 20. Does that look right? All right, so let me go ahead and write this guy down. So it says for this one, we want to solve the initial value problem. And then we want to find the interval of validity of the solution. All right, so we have y prime equals 2y minus y squared, and y of 0 equals 1. All right, well, let's start with the, I don't know, what do you want to do? You want to solve it first or talk about what we know? You know, let's talk about what we know in terms of solutions to this. Like, are we guaranteed a solution? If we're guaranteed a solution, is it the only one? All right, let's just sort of talk about that right now. Okay, so here's our differential equation. So let's just start with existence and uniqueness. So remember the trick, or not the trick, but what the theorem tells us to do is once we've got it as y prime, this thing is our f of xy. And so it's that and it's partial with respect to y that tell us everything about solutions and all that. So let's start with existence. So we just need to know about f of xy. Is this thing continuous?
Yes, it's continuous.
Okay, yeah, that's an easy one. It's like, yep, we're all good. So no matter what, there's never going to be a point that you give me, an initial condition that you give me that's going to run in any kind of problem of there being a solution. So there will be a solution to this initial value problem. All right, so then the next question is, what about uniqueness? So for the unique, well, this one, we need to look at Fy. So the partial with respect to y is 2 minus 2y. So same question, is it continuous? And the answer is same as before. So yep, again, all good. So what does this tell us right now?
There is no unique solution.
Okay, so we know that there is a unique solution. And it didn't matter at all what our initial condition was. Since it's good everywhere, since both of these are continuous everywhere, we know there's a unique solution. But remember, this means a unique solution on some interval that contains this point. It doesn't necessarily mean that the solution we find is going to work for minus infinity to infinity or anything like that, right? We know that there is an open rectangle that contains this point where there is a unique solution. And I know that there's a sub-interval, but what exactly it looks like, well, we're going to have to figure out.
I have a quick question.
Sure.
I know the theorem says that there will be a unique solution over some subinterval, but if it is continuous in both respects, would it be from minus infinity to infinity as well?
Not necessarily.
Okay.
I mean, that's the thing, is that I can build basically an infinite rectangle, right? Like around this point 0, 1, your open rectangle can be as large as you want, and so it could basically, for all intents and purposes, go to plus or minus infinity. But the theorem doesn't say that that solution will exist over that entire rectangle. It just says that somewhere in that rectangle you can build an interval around it. So we have to be careful. Just because this is saying that you could have an infinitely large rectangle doesn't mean that the actual location of the solution has an interval that's from minus infinity to infinity. All right, so now that we've talked about it, let's solve it. So how are you going to solve this differential equation? What type is it?
It's a separable.
It is separable. Good. This is the one where we can rewrite it. So we've got our y prime over 2y minus y squared equals 1. And now we can integrate. So over on this side, we're going to get our x plus c. And then what do we get on the left-hand side? Well, if this was first year calculus and we had to actually like integrate it, we'd use partial fractions. This is one where you would split it up into partial fractions, do both of them, but that's not this class. So let's just go ahead and use our trusty, I'm using my TA89 here. Let me see what this gives me. Squared comma x. All right, so I get a minus 1/2 natural log of y minus 2 over y. And of course, these things are in absolute values. So they should each be, you know, hold on, that's all gross. Let's try this again. Okay, so we have minus 1/2. I'm actually going to leave them separated. Let me write as natural log of x minus 2 minus the natural log of x. And that equals, dang it. That should be y's. Y minus 2 minus natural log of y equals x plus c. All right. Yeah, no. Hold on a second. I don't like this. Let me real quick just, when in doubt, let's do the freaking algebra, right? So it's y times 2 minus y, so a over y plus b over 2 minus y So a times 2 minus y plus by, that has to equal 1. So when y is 2, b is 1/2. And when y is 2, or when y is 0, then a is 1/2. Okay. So we have 1/2 natural log of y minus 1/2 natural log of 2 minus y. I like that a lot better. Let's write it like this. Okay, so regardless, we get our integral and we're here. So now let's get our initial condition by plugging in our point. So y of 0 equals 1. So we're going to get 1/2 natural log of 1 minus 1/2 natural log of 1 equals 0 plus c. Well, the natural logs of 1 are zeros. So that gives us c equals 0. So we have 1/2 natural log of y minus 1/2 natural log of 2 minus y equals x. Okay, so there's our solution in the implicit form. We could go ahead and find this explicitly. You can combine these logs, multiply the 2 to the other side, then run the hook. And then if we just do a little bit more algebra real fast, we're going to get y equals 2e to the 2x minus y e to the 2x. Moving that over, factoring out I think we're here. Don't quote me on that, but I'm pretty sure that that's what the solution is. Okay, so now let's go back to what's the validity of this? What is, like, where is this thing okay? Well, in terms of the domain, the e to the 2x's were all good there. And so it turns out that this is good for all x. So we can be for our x's between plus and minus infinity. So this one, it does turn out that the subinterval is actually the entirety of it, but we don't know that going in. There is the potential that it doesn't play out that way. So then what about the y's? What happens with the y's here? Can you see what happens? How about what's the limit as we go to infinity? You guys there?
I'm thinking.
I'm here.
All right, so I'll tell you what. Let's go to Desmos, and we'll draw the graph so we can see what that looks like. All right, so we had y equals 2e to the 2x divided by 1 plus e to the 2x. All right, so you can see that it does go through our point 0, 1. And notice that there's a horizontal asymptote at 2. if you divided everything by e to the 2x, you would get 2 over 1 over e to the 2x plus 1. The 1 over e to the 2x is going to go to 0, so you get 2 over 1. And then if you go the other direction, the e to the 2x's go to 0. You get 0 over 1, which is 0. So notice that this solution is good for all x's, excuse me, but the y's are only good between 0 and 2. So even if you kind of go back to that idea of the infinite rectangle, our solution doesn't live in an infinite rectangle. It's only in this. So there you can see at least a restriction on the y's that comes about just from the structure. But if you go back and you look at our solution, I think I had that on the whiteboard. Let's see here. Where's yeah, come back to this piece right here. I mean, I guess you can see it on where the C is gone, but if you look at this, you can see why we're trapped where we are. Natural log of y is only defined when y is greater than 0. Natural log of 2 minus y is only defined when y is less than 2. So we're trapped. And 0 and 2 are actually problem spots when we divided by the 2y minus y squared. So we can see why that's an issue. But those issues have nothing to do with the existence and uniqueness theorem. They're just products of what this thing actually looks like. Anyway, so is that better for number 20? Is that kind of what we were looking for, Victor?
Yeah, the process is clear, but the explanation of that rectangle, that was what I'm looking for.
Okay.
And
So the rectangle is just giving you it's the fence that makes the field. And we know the solution is somewhere in that field. Right?
But what if I want to go yard?
Well, you can't do that in this game, especially if this field is infinitely large. So, but the Padres definitely have enough people to do that.
Yeah, they do.
I'm excited for that team, actually. Not gonna lie.
Me too. The only thing that concerns me is how the pitching will compare to that of the Dodgers.
Yeah, that's a good point. All right, so any other questions on the homework, or is that good? And if you haven't gotten into it yet, obviously I understand that. We have more opportunities to talk about it later, so that's not that big a deal. Okay, so we're going to look at some other kinds of equations that we can pull some tricks on to make separable. And then we'll also look at a new type called exact. All right, so let's do that. But you know what? I'm kind of liking being just sitting here today. So I think I'm just going to share off the computer whiteboard. But let's talk about some other forms that become separable. All right, so here's a new type of equation for you. These are differential equations that are called Bernoulli equations. So you probably know that name. For you that have taken physics, Bernoulli's equation, or there's a different Bernoulli, by the way. Same family. It was two brothers and a father, and I forget who's who, but one of them was the physicist Bernoulli that came up with, the relationship between like fluid pressure flow and things like that. And then the other two were mathematicians. One of them was a probability person. So if you've taken stats and you've talked about the Bernoulli distribution, that was that one. But the other one of the three came up with this. So a Bernoulli equation, this is a type of differential equation. And the way that they can be written, or they're the ones that can always be written in this way, where we have our y prime plus p of x y, p of x times y. But then what it equals is a function of x, we'll call it f of x, times y to the r. All right, so that's just the form for a Bernoulli equation. So notice that this is a non-homogeneous form that kind of stems from the linear first order homogeneous, right? Like if we just make this side 0, that's the same kind that we learned how to solve, last week. All right, but this one's got a very specific form, f of x times y to a power of r. So if r is 0 or r is equal to 1, we're not going to consider those. And hopefully you can see why. If r equals 0, what this form turns out to be is y prime plus p of x times y equals f of x. And that's just a linear first order non-homogeneous. So we don't need to reinvent the wheel. We already know how to solve those. Similarly, if r is equal to 1, that looks like this. And this one, if you just do a little bit of algebra, I mean a real little bit, just move the f of x guy over here. Notice that this is a also linear first order, but now homogeneous. And again, we already know how to solve those. So we're not going to concern ourselves with the r equals 0 or the r equal 1 case because, yeah, we already know how to do those. Okay, so here's a Bernoulli equation. Now, we're going to pull the same trick that we've done a few times now, where we're going to find a solution to the homogeneous. Okay, so we're going to find a solution to homogeneous. And we're going to call it y1. So you just pretend that this side is 0. We know how to find the solution. We're going to call that y1. And then what we're going to do is we're going to guess a solution of u times y1. So if this looks familiar, it should, because that's actually how we developed the finding the solution to the non-homogeneous, right? So this trick, integrating factor trick, I think I mentioned this before, is super common. We're going to run into it very frequently during this course. All right, well, let's see what happens if we pick y equals u times y1. So we'll go ahead and put that back into the differential equation here. So y prime is going to be u prime times y1 plus u times y1 prime. And then we're going to get plus p of x times u times y1. And that's going to equal f of x times u times y1 to the r. All right, so now let's distribute a little bit, group things. You'll see why here in a second. Okay, so this is going to be u prime y1 plus u times y1 prime plus p of x times y1. again, equals f of x times u times y1 to the r. Sorry about that. Let me actually just do this. Let's write it as u to the r, y1 to the r. All right, well, same thing happens here that we ran into before. If you look at what's in the parentheses, or sorry, in the brackets here, that actually is going to equal 0 because of the fact that y1 was a solution to the homogeneous. That's why this integrating factor thing works out a lot, especially if it's when we're multiplying to the solution to the homogeneous. So that thing goes away. And now you'll notice we've got u prime times y1 equals f of x times u to the r times y1 to the r. And it turns out this thing is separable. We get u prime over u to the r is equal to f of x times y1 to the r minus 1. So that's why this is going to be okay, is that when we do this integrating factor, it turns it into a separable differential equation. So that means now we can actually solve for our u, right? Because you can integrate, and then once you've got that u, you just multiply it to your y1, and we've got our solution. So I guess I'm going to add to that list of what we're doing, right? So the first one was we find a solution to homogeneous, then we guess a solution. Then we're going to find u. And I'll even put here using separation. And then lastly, you're going to get your y. So I'm going to substitute this into the y. So very procedural, just like all the others. It's just a different process. Okay, so here are our steps. This is what we're going to do. So let's do it. So let me show you an example. I'm going to keep this bit on here and keep our original, but the rest of it I'm going to erase because we don't really need it right now.
I know we're about to do an example, but where it says
Yeah.
guess the solution of y equals u times y1,
Yep.
is that the same way of doing it as we did before?
Yep, exactly. It's just how we find u is a little bit different. Yeah, you guys are going to get, I think you're going to get really tired of this method of the old, oh, let's multiply by u and see what happens, because we're going to do it so often. It's just different forms of the original differential equation will lead to different processes for finding the u. And, you know, that's where the variety comes in. But this process, this, you know, make a guess by multiplying by some unknown function works really, really well in lots of situations. All right, so let's do this. Let's try this out. All right, so here's an example for you. Let's say we've got y prime plus y equals xy cubed. So you can look and see that this is definitely of the form, right? If we wanted to just sort of translate here, so p of x is 1. f of x is x, and r is 3, right? So that's how you can read this as it's a Bernoulli equation. And as it is, it's not separable. It's not linear because of the y cubed, right? So we don't have a way of dealing with it. But luckily, we've got Bernoulli, and Bernoulli will help us here. All right, so I'm actually going to start building this for our separable. So here's what we're going to have. We're going to have the integral of u prime over u cubed. That's going to equal the integral of x times, well, something to the r minus, oh, shoot, get rid of, we already know what the r is. So r is 3, so it's going to be something squared. So we just got to figure out what that something is. And again, that y1 is a solution to the homogeneous. So let's go find that. So if we go to the homogeneous, y prime plus y equals 0. Remember the trick for this? Y1 is going to equal to e to the negative integral of p dx. So y1 is going to equal e to the minus x. So that's what goes into our brackets here.
Does that negative come out, or is it 1 over e to the x?
That's 1 over e to the x. So let me rewrite this. So we have the integral of u prime over u cubed equals the integral of x over e to the 2x. Or, you know what, no. We'll write it as multiplication. It doesn't really matter, but. All right, so now we're ready to go. Let's integrate. So u to the minus 3 becomes a minus 1/2 u to the minus 2. And then on the other side, if you were going to do this the long way, and I'm not gonna, let me go ahead and use my calculator. But if you were going to do this the long way, this would be integration by parts, right? You remember your good old UDV business. So you'd need to use integration by parts, but like I said, I'm just going to jump right to the TI-89. And what I get here is a minus 1/2 x e to the minus 2x minus 1/4 e to the minus 2x. And again, let's put in our plus c. All right, so we'll go ahead and solve this for u. Let's multiply everything by minus 2 just to get rid of all those fractions. So we get 1 over u squared equals x over e to the 2x plus 1 over 2 e to the 2x plus c. I'm going to go ahead and combine all those into one fraction. So I get 1 over u squared equals 2x plus 1 plus CE to the 2x all over 2e to the 2x. I know technically that would have been a 2c, but since c was arbitrary, it's still c. And I put this all into one so I could get u squared. I could just flip it over. So then u is going to be the square root of this. All right, so are we okay with u? Okay is maybe not the right word, but
Yeah.
see how we found it. Okay, I'm going to do one more thing, just to you'll see why. I'm going to actually factor out that e to the 2x, because the square root of that is just e to the x. And you'll see why I did that when I go to my next step. All right, so there's our u. And again, remember what we're doing is we're trying to find the solution. And the solution was this u is the thing that gets multiplied to our y1. So if we put this all together, here's what we're going to find. Our y then is going to be y1 times this. Well, the e to the minus x and the e to the x cancel. So there is our solution. There's the general solution to this differential equation. And yes, I know it's ugly, but if you take a derivative, add it to itself, put it in here, you'll see that you actually get truth. So the key to Bernoulli's is just recognizing that it's Bernoulli. Being able to strip all this stuff off so you get your P, your F, and your R, and then just put it into the form and just go. All right, so what do you think about this method? Are you going to be able to replicate it?
With practice, sure.
Yeah. Okay, so what was the hard part of this?
Yeah,
Algebra.
Yeah, like always, right? It's not the actual differential equations. It's not the integration. It's the stupid algebra. And I mean, that's pretty much been how it is for you guys ever since you learned algebra. What makes math hard? It's all the algebra. And I don't know that it's necessarily hard. It's just long and tedious and lots of places to make mistakes. And you slip up one spot and the next thing you know, right. But it's a process. All right. So if you've got something that's Bernoulli, my recommendation is literally do what I did. Write out, here are the different pieces. And then you can put them into your form, because the form is always the same for the separable. It's always u prime over u to the r. And the other side is going to be f of x times y1 to the r minus 1.
So what happened to the e to the x times our square root? What happened to the e to the x?
Okay, so I talked through that when I was over here with the y equals. Remember that it's u times y1. So
Yeah.
So I had, let me write it in the opposite order. So I've got my y1 is e to the minus x times my u, which is e to the x times the square root of all this stuff. Right?
Yeah. Okay.
And then if you just do those two rules of exponents, right? Add the exponents together, x minus x is 0, e to the 0 is 1. So it ended up just canceling.
Okay.
And we're left with just the radical. I just saw that coming, which is like when we got over here, I thought that that was going to be useful. So that's why I pulled it out. If you don't see that, that's, I mean, that's totally fine. If you had written your answer as e to the minus x times this thing that we had on the second to lines or second to last step, I would be totally okay with that. These are just things that hopefully by now you're starting to spot a little bit ways that you can simplify, because if we can, I mean, we want to, right? I would rather just have this square root than all that other nonsense still part of it, right? So the goal should always be to make it as simple as possible, but I'm not going to penalize you if you don't see it, because right now I want you to learn the process, right? I want you to learn how to do this stuff. The simplifying, I know you can do in a pinch.
Bernoulli equations are not linear, right?
Correct.
Okay.
Yeah, but by definition, they're not linear because of the y
The
to the
R.
r,
Okay.
right? This makes them nonlinear. They're linear if r is 1 or r is 0, but that's why we don't actually include them in this, because when r is 1 or r is 0, we've already dealt with solving those guys. You know, they're nonlinear. They're also not separable, but they can be turned into separable using this little trick. All right, so other questions on this one before we boot it and look at another? All right. 3, 2, 1. All right, there you go. Okay, so Bernoulli equations. It's another form that we can actually deal with if we play a trick. All right, now the next set I'm going to show you, and don't get mad at me about this. Okay, it's not my fault that we call it these. These are also called homogeneous. But I'm going to put here in parentheses, not homogeneous. That's a little joke. Okay, so these are another type of equation that are called homogeneous. But they are not what you think of as homogeneous. Again, it's not my fault. I swear to God, I didn't come up with this. Okay, so this kind of homogeneous means that y prime is a function, I'll call it q, of y over x. All right, so first of all, you can see why I'm saying it's not homogeneous. It's not equaling 0, right? So this means a different thing. It's just specifically this function is a function of y over x. So an example would be something like y prime equals y cosine of y over x all over x. This is one of these new homogeneous equations, because you can think of it as y over x times cosine of y over x. So basically, you could do a substitution of u equals y over x. And you've got your function. So for certain elements, it's pretty easy to tell. Like the cosine part, it was pretty obvious that it's y over x. The other part, maybe not as obvious, but they can get even worse. Like suppose I have this. All right, whoops, not minus. And divide. No, that's not what I wanted. Shoot. Hold on. I'm trying to get too so much for erasing. I'm trying to get too fancy here. How about this is what I want. Natural log of x minus natural log of y. Right? Because if you look at this one, it's not obvious that it's a function of y over x. If you combine the logs, you get natural log of x over y, which is closer. But we would actually have to do one more step here to make it a y over x. All right, so at the beginning, it definitely didn't look like one of these new homogeneous, but it absolutely is if you do some algebra on it. All right, so sometimes these are hard to spot. Sometimes they're hard to see exactly, but they're another kind of form. All right, now, the trick for these, for the new homogeneous, is you're going to let y equal u times x, where u is some function of x. Because watch what happens. If we do this, y prime is going to be u prime times x plus u. This is the product rule. The derivative of the first times the second plus the first one times the derivative of the second. The derivative of x is equal to 1. So if you do that, this is going to give you u prime times x plus u equals q of u times x over x. All right, so those x's are going to cancel. So we've got u prime times x plus u equals q of u. So what is this u? Don't really know. But I know that if I multiply it by x, that's my solution. But this thing right here is actually separable. If I move the u to the other side, just do minus u. And then I can separate it by making it u prime over q of u minus u equals 1 over x. And at this point, we know what to do. We're going to integrate, and then we're going to find u. All right. Well, the point of this is same thing as before. By doing a little trick, we're able to make it separable, which means we can actually solve these things. All right, so I'm going to make one of these up. I'm a little scared to do it, but you know, what the hell? These things happen. We'll see what occurs. So here's what we're going to do. Let's say we've got y prime equals. Let's go with secant of y over x plus y over x. I'll make it terribly obvious that this thing is one of these new homogeneous, right? Hopefully that's obvious. You all see it. So if we were to do that u substitution, if we let u equal y over x, right, that's what this is saying. Think about what this form looks like. This is secant of u plus u. So that's basically the idea with one of these new homogeneous, is that if you let u equal y over x, it turns into just something of u. So this guy, that's our q of u. All right, so let's go down to what we have to do to separate these things.
I have a quick question.
Yeah, go for it.
Why is it the form it's in right now not good enough to just integrate?
As it is right here.
The secant of u plus u.
That one you can integrate, but the problem is this isn't just y prime anymore. Because when we change it to the u's, remember the y prime turned into u prime x plus u?
Oh, okay.
And so like integrating that's not something that you do because it's not just a derivative. But we saw that with the substitution, we can jump straight to this form. So it's going to actually look like u prime over secant of u plus u minus u equals 1 over x. So let's simplify this a little bit. So we get u prime over secant of u. And 1 over secant, of course, is cosine. But we're here. And now let's integrate. All right, so the cosine of u, that becomes sine of u. The 1 over x becomes natural log of x plus c. So again, I want to get u. So u is going to be the inverse sine of natural log of x plus c. Now, that's not my solution though, right? My solution is y equals. So if you come back over here, you can see that y is equal to u times x. So if we jump back to that for our solution, then y is going to equal x times the inverse sine of natural log of x plus c. So this is a solution to our original differential equation. Okay, so it's another form that leads to separable. We have to pull a trick on it, just like we did the other one. And it's even sort of that integrating factor trick, right? I mean, we still have here u times x. It's just not u times y1. There's no y1 defined. But it's that same idea of, well, let's take a form that's some multiple of something else. Because if we can find that u, then we can multiply it by that other thing and get our solution. All right, so these homogeneous that are not homogeneous like you think of as homogeneous still are doable. They always lead to a separable form, right? In fact, it's this thing right here that always comes up when it is one of these new homogeneous. All right? So take it for what it is. It's yet another form that we can take care of. I don't know if you remember this. Just a real quick aside. I don't know if you remember this, but like day one, when we were talking about diffie-qs, I mentioned how this was all pattern recognition. It's all about looking at the equation and figuring out what the form is. And hopefully you're starting to see what I mean by that. Like we're learning all these different techniques to solve differential equations, but they're all dependent upon being in the right form. Like all of them. The two that we've seen so far today, the homogeneous, the new homogeneous, and Bernoulli, those have specific forms. But so did all the other ones. The linear first order, very specific form, whether they were homogeneous or non-homogeneous. The separable, that's a very specific form. You have to be able to write it as function of y on one side and function of x on the other. So, and this isn't going away. This isn't going away. The difficulty for sure with differential equations is looking at the very first thing and going, all right, which of the very many forms is this? Because once you figure that out, once you determine which form it is, you can go to your recipe for that type of differential equation. And those recipes are all different, right? And they're all different because they have to be, because they're different forms. Yeah, it just is what it is. And that's the thing about differential equations. And you know, for me, you guys know me. This is just, I mean, monkey math, man. It's just like, all right, I do my one moment of non-monkeyness, which is figuring out what type it is. And then I just turn into the math monkey and I just run it. I just do my numbers, do the process. So for me, I'm not a huge fan of diffie-qs. I'm not. I mean, I know how to do them. I can do them. I will do them. But they're not fun and exciting. They're not like trig. Like you guys know with me and trig, oh man, I'll do trig stuff all day long. I find it super interesting, even though I guess you could say that's also really procedural. But this one, like diffie-qs, like totally just monkey math. Anyway, so speaking of being good little monkeys, let me go ahead and show you the next type differential equation, the next form that we're going to tackle. All right, so these, let me clear all this nonsense. This type, these are called exact. All right, so exact differential equations. All right, now what do these things look like? All right, well, the form for these is you're going to have some function. Let me think about how I want to letter these. Let's do f of xy plus some other function, g of xy, times y prime equals 0. All right, but there has to be something very special about f and g. F has to be the partial derivative of some other big function that we're going to call big F. All right, but it's going to be the partial with respect to x of this big F. And g is going to be the partial with respect to y of that big F. All right, so these aren't just any old functions that are, being multiplied in this way. They are very specifically the partial derivatives of something else. All right, now, if you look at the book, and I think this is pretty common in lots of other places, you'll see this written as m of xy plus n of xy times y prime. But you still have that where this m is the partial of something with respect to x, and the n is the partial with respect to y of that same function. All right, so let me show you an example of one, just so you can see what I mean here. So let's say that we've got 3x squared plus x cubed times y prime. Oh, sorry, 3x squared y plus x cubed times y prime equals 0. Now, I totally admit that this one is one we already know how to solve. I don't know if you notice this is a linear first order, but I just want to point out that this thing is exact. So here are your m's and your n's. Okay, so m is 3x squared y, and n is x cubed. We're using this notation. But here's our big F of xy, the thing whose derivative with respect to x is 3x squared y, and whose derivative with respect to n is x cubed, is going to be x cubed y. Right? Differentiate this with respect to x. 3x squared, and the y is constant, so 3x squared y. Differentiate this with respect to y, x cubed is constant. And then the y goes away. All right, so this is an example of one that is exact. Well, obviously, we don't need to use the technique for exact differential equations because, like I said, this is linear first order. It's because I wrote it in kind of a backwards way. Right? I could even divide by x cubes. So this is actually homogeneous linear first order. And that guy's really easy to do. Right? We know exactly what we need to do to solve it. All right, so this is how you're going to recognize it, is you're just going to look for whatever's being multiplied to y prime. Think of that as your partial with respect to y. And the other one needs to be your partial with respect to x. Does this look familiar to you?
Which part exactly?
This whole, like, there's a partial with respect to x and a partial with respect to y from some function. Like, do you remember seeing that kind of thing before?
Yeah, with like tangent planes and stuff.
Okay, so back in the day with tangent planes and whatnot.
Yeah.
Specifically, it was gradients. Right? I mean, that's the gradient of something. So if, just on an aside, if we look at this big F of xy, the gradient of F was 3x squared y comma x cubed. And this vector, right, it's a in the x, this piece is in the x direction and this is in the y direction. So you could really think of that as with like a little dx and a dy. Well, let me just kind of carry that on here for a second. So we sort of have a 3x squared y times dx plus x cubed times dy. And if you were to divide by the dx, you can see how this now all of a sudden takes on that form. So what we're really doing is we're looking at some function and we're taking its gradient, we're taking its derivative. Well, that takes care of this left-hand side. What about the right-hand side? What are we differentiating to get 0?
A number.
Yeah, just any old constant number that you want. And so what we just did, we basically talked through what the solution is. The solution to this is f of xy equals c. So in order to solve an exact differential equation, all you got to do is figure out what function was it whose gradient was taken to give this form, and you set it equal to 0. So think about this. We found that f of x, right? It was x cubed y. So that tells me that the solution is x cubed y equals some constant. That's the solution to this differential equation. I could even solve that for y and get c over x cubed. But that's the solution to this guy. Now, let me show you that we would have gotten the same solution if we had solved it as a linear first order. If we had recognized this, we go, okay, so y is going to be e to the negative integral of 3 over x Well, 3 over x gives us 3 natural logs of x. So we get e to the minus 3 natural log of x plus c. So we can pull that c out front. We can bring that minus 3 in as an exponent. The e and the natural log cancel. Hey, wait a minute. Same. So this one, I showed this to you for a reason. One, it's pretty easy to figure out what that function is, whose gradient was the original differential equation. But it's also one that we can solve in another method. So you can see that, yeah, this is totally valid. All right. So exact differential equations, the key, like what the important piece is looking at these two things and seeing that they are the gradient of something else. All right. So here's total review for you guys. Do you remember how to tell if these are your gradient or other language? This was this guy x cubed y. This came from a conservative vector field, and we called that a potential function. So remember back to the fall? Probably not. Back in like October, November. You guys were with me. Don't make me feel bad. But you kind of remember that? Talking about conservative vector fields?
Slightly, yeah.
Slightly. Yeah. Do you remember how to check if a field is conservative? Man, there's all kinds of pressure on you now. And each second that goes by makes me a little bit sadder and deader inside.
I think it has something to do with you can differentiate it or integrate it.
Okay, so the check is definitely a differentiation check. Yep. You do partial integrals to find the potential function, but to know that it even exists, you do a differentiation check. All right, so I'm just going to remove the torture. Do you remember that thing called curl? Not what it is exactly, but you remember curl.
Yeah.
Right. And curl was literally a measure of how curvy a vector field is. Well, the way to check if something was conservative was to look at the curl and see if the curl was equal to 0. All right, well, I just mentioned that, and I imagine some of you are going, oh yeah, I kind of remember something along that. But if I asked you to find the curl, you'd be like, I don't know. So here's actually the check. All right, here's what you can do to see whether or not it is exact. All right, so to be exact, you need the partial of m with respect to y has to equal the partial of n with respect to x. So if we come back to this one, let me just.
I do remember that now.
Okay. I figured it was just a matter of seeing it again and you'd start going, oh, yeah. So here we go. So if we look at my, that's going to be 3x squared. If we look at nx, that's 3x squared. Oh, hey, look. Those things are equal. So I know that there's a potential function. So this is how you're going to check. This is how you're going to look at one of these things and go, all right, is it exact? You're basically going to take the curl. This would be why it's a good idea to take vector calculus before taking differential equations. Just like there's benefit to taking linear algebra before differential equations, as we've already kind of seen. it's the story of math, right? Everything kind of builds on itself. Anyway, so that's going to be the test. That's what we're going to do. And then if you actually want to find it, remember what you're doing is you're integrating m with respect to x, and you're integrating n with respect to y, and you're combining those. Anything that's in common to those two, they only show up once. But what can happen in the first one, you can get some functions that are only x's that go away when we find our n. So we need to include those. And then similarly with the second one, you can get some functions that show up that have y's, and you need to allow for those to be there as well. All right, so let me show you another example. And this one will actually run all the way through. We'll first show that it is exact. Then we'll find the potential function. We'll take that potential function and we'll set it equal to c. And there's our solution. Okay, so let me go ahead and erase all this stuff real quick.
To find f, when we integrate with respect to m, with respect to x, and so on, do we multiply them after, or do we add them?
You add them.
Okay.
All right, so here's an example. And let's see if we can find the solution to this. All right, so first of all, let's just go through our list of classifications and all that. It is first order. We got a y prime. It is not linear. How do you know that this is not linear? Just by looking at like what jumps out at you.
Cosine of y.
Cosine of y. Okay, so it's non-linear. So all those techniques are gone. Is it separable? Oh, hell no. Yeah, like do your best to get the x's and y's not attached. You got no chance. Okay, so it's not separable. You think about the forms we just looked at today so far. Is it Bernoulli? No. Cosine of y definitely tells us it's not Bernoulli. And then is it one of the new homogeneous?
Not even close.
No, again, it's not cosine of y over x, and there's no way we're going to make it a cosine of y over x. So it's none of the other forms. But it definitely has the potential. Get it? It's got the potential of being exact. So here's the question. If it's exact, this is our m, the 4xy plus 1. And then this is our n, 2x squared plus cosine y. So let's check it. Let's look at the partial of m with respect to y. All right, so the 4xy becomes a 4x, the 1 goes away. And then we need to look at nx. Okay, well, 2x squared, that becomes a 4x. Cool, so far so good. And then cosine of y goes to 0. All right, so this is when we get happy, big old grins, because my and nx are identical. All right, so let's get our potential function. So I'm going to start by integrating m with respect to x. Okay, so the 4xy, the 4x becomes an 2x squared, and the y is constant. That's going to be 2x squared y. And then the 1 becomes an x. So again, this is a partial integral. So everything that's not x is just constant.
Do we have the plus c with partial integrals as well?
We're not going to do that here. I mean, yes, we do, but that constant, it's actually, it's a function of y. You would write it as some constant function of y. It's not just going to be a number. I mean, it could just be a number, but it could also have y's in it.
Because we treated y as a constant.
Exactly. When
Got
you
it.
do partial derivatives.
Got it.
Okay, so I'm not going to put that in there because like the context of what we're doing with potential functions, we don't need it. Okay, so then let's do the same thing with the n, but with respect to y. So 2x squared is constant, which means we get 2x squared y. And then the cosine of y turns into a sine of y. All right, and then you can make the same argument here. This one, though, is going to be some constant function of x, because again, x's are going to go away when you differentiate with respect to y. But not germane to the argument here. Okay, so now to get our potential function, we're just going to combine these things. So the first one needed a 2x squared y and an x. The second one needs a 2x squared y, which we already have, but it also needs a sine of y. So that's how you put these together. You just literally take all the pieces and add them up. And anything that's in common just shows up on that list one time. So this is a function whose derivative with respect to x is 4xy plus 1, and whose derivative with respect to y is 2x squared plus cosine y. Okay, so all of this that we just did should feel really familiar because you did this back when we found potential functions for fields. We did this sort of thing when we did line integrals. You may remember, like if we wanted to calculate the work going from point A to point B over a field, if it was conservative, we could find this function and then plug in the endpoints and subtract, use the fundamental theorem of line integrals. I'm just throwing out as many terms as I can to try to make those synapses click in your brain. And so you go, oh, yeah. All right, so if I just said all that and you went, holy crap, I don't even know what you're talking about. I want to say it was chapter 14. It's the last chapter of calculus where we do that. Anyway, now let's solve our differential equation. So the solution is going to be this potential function equals a constant. And there you go. That's the process for exact differential equations. So in my experience with DiffyQ students, y'all like this one. You like this method for a couple of reasons. One, you've just been going through the ringer with all these weird different variations that often require some sort of multiplication trick and blah, 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 right? This is really straightforward. But the second reason that y'all like this is you've done it before. You may not remember that you've done it before, but you've done all these pieces before in a different context. So it's sort of familiar. And isn't that kind of the story in life? Like when you run into a situation that's like one you've already done, you're more comfortable in it, right? You're
For
like,
sure.
you know, it's like, oh yeah, I've already been to a party where I don't know anybody, but I had to go with my, you know, boyfriend, girlfriend, whatever, right? You do that a second, third, fourth time, it's not as awkward as the first time. And it's the same deal here, right? So I think you guys are going to like these because they're familiar. You've done similar things before. So you kind of know what to expect. You kind of know the steps. You kind of know the process, and everything is good. Okay, so let's try another one. Let's do another one here and see how this one goes. All right, so let's try this. Let's go with y plus 2xy minus e to the minus 2y. Actually, hold up. I don't want to do this one. No, hold on. This one requires a little bit of a trick I don't want to pull on you yet. But we don't have enough time for it today. We'll do that one next time. So how about this one? Let me change it a little bit. We'll go with a audible here. Let's go with e to the x plus y plus y e to the x. Hold on. I'm getting way too fancy here. Hold on. All right, so I'll go with e to the x plus y. And then over here, we're going to have plus. Let's go e to the y plus x times y prime equals 0. Okay, so again, it's definitely not linear. E to the y, separable. I don't know, maybe not. Is it Bernoulli? Absolutely not. Is it the new homogeneous? Again, possibly, I don't know. But let's just see if it's exact, because if it's exact, then we should be good. Oh, shoot. Sorry about that. I went to go move one of my windows and I accidentally hit the close on that guy. All right, so there's our differential equation. So now let's do the same thing. Let's look at, here's m and here's n, and let's check them real quick. So my, well, the e to the x goes away, y gives us 1. All right, and x, e to the y goes away, x gives us 1. Cool. This thing is exact. All right, so now let's integrate m. So the e to the x plus y, let's integrate that with respect to x. So that's going to give us e to the x plus xy. And then we integrate the n, e to the y plus x, with respect to y. So e to the y, of course, is e to the y. The x gives us xy. So we'll put those together. We get e to the x plus e to the y plus xy. So that's the function whose partials were m and n. So then the solution to this differential equation is e to the x plus e to the y plus xy equals your favorite constant. There you go. Done. There's our solution. So notice that it's exactly the same process. You do exactly the same thing. And once you get that potential function, you just set it equal to C.
To check if we're correct, do we partially differentiate with respect to both, or do we just do one of them?
So you would have to do a gradient.
Okay.
Find the gradient of both sides, because that's what this is. Like if you go back to these original ones, like this guy, this is the result of taking the gradient of the 2x squared y plus x plus sine y. And this is the derivative of 0. Or maybe a better way of saying it, again, I don't know if you remember this, but back in the day when we were looking at line integrals and work and all that, one of the forms was what we called the differential form for the field. And the differential form of the field is the differential equation, basically. So if you want another justification for solving differential equations, it was given a vector field, find the potential function. Or given a conservative vector field, find the potential function. You were solving differential equations back then. We just didn't tell you that. Just like when you first learned to integrate and you integrated cosine of x and got sine of x plus c, you were solving differential equations. We just didn't tell you that back then. So anyway, so these are exact. Now we're still going to talk a little bit more about them. I'm not today. We're going to go ahead and end here, but we're still going to talk a bit more about them because there are some tricks. And like I started writing one up and I went, oh wait, no, I don't want to do this one, because there are tricks that we can pull that can take things that are not exact and make them exact. I bet you can guess what that trick's going to be.
We're going to pretend.
And we're going to pretend that we know a solution. And we're just going to do the whole, well, let's multiply by u and see what happens. We're going to go, okay, you know what? This equation isn't exact. But what if I were to multiply the entire equation by something called u? Can I make it exact? Right? So, oh yeah, you can see the shit-eating grin already coming up because, yeah, that's what we do. We're always about, nah, let's just wing it. Let's just fake it. Right? Mathematicians, oh man, they are definitely the definition of fake it until you make it. Right? What's the solution to this? Oh, I got your solution. Oh yeah, what is it? Well, hold on, let me make it. I'll get there. Right? But we go in with such confidence of, yeah, we'll just take this and we'll multiply by u and we'll make it this form. And then we tend to luck out a lot with that and go, all right, cool, that works. So that's what we'll do on Friday. We'll look a little bit more in depth at these and look at some of the tricks that we can pull when they're not exact. But also we're gonna have oh no, we're not. We don't have any quizzes in this class. Never mind. I was thinking about physics, so never mind. I was going to tell you get ready for a quiz on Friday, but we don't have any quizzes in DVQs. So I think other than that, I'm just going to let you know that you're probably good on homeworks through. Let me double check what section that is. You should be good through 2.4. So I think we're still just slightly ahead of schedule, and I figure as long as we can continue that, we will. But you should be good with homeworks through 2.4. All right. So with that, have an awesome couple days, and I'll see you all on Friday, except for the handful of you that I'll see tomorrow in physics.